my name is David López.
Hi, my name is Carlos.
Hi guys, my name is Andrés, and in this video we are gonna do a little explanation of how to draw a Bode diagram for a transfer function with complex conjugated poles. So let's start with some theory.
A transfer function represents the relationship between the output signal of control system and the input signal for all possible input values. A block diagram is a visualization of the control system which uses blocks to represent the transfer function. An arrow which represent the various input and output signals. Thus, the cause and effect relationship between the output and input is related to each other through a transfer function. In a Laplace transform, if the input represented by Rs and the output is represented by Cs, then the transfer function will be this. But really, what is the transfer function? The transfer function of a control system is defined of the ratio of the Laplace transform of the output variable to Laplace transform of the input variable, assuming all initial conditions to be zero. Procedure of determining the transfer function of the control system are as follows. First, we form the equation for the system. Second, now we take the Laplace transform of the system equations assuming initial conditions as zero. Third, specify system output and input. And fourth, lastly, we take the ratio of the Laplace transform of the output and the Laplace transform of the input, which is required transfer function. Poles and zeros of transfer function. Generally, a function can be represented to its polynomial form. For example, this. Now, similarly, transfer function of a control system can also be represented as this, where k is known as the gain factor of transfer function. Now, in the above function, if s is the same as c1 or s is the same as c2 or s is the same as C3, the value of transfer function becomes zero. Thus, C1, C2, and C3 are roots of numerator polynomial. As the these roots the numerator polynomial, the transfer function becomes zero. These roots are called zeros of the transfer function.
As an example, we have this transfer function. To draw the Bode diagram, we first have to get that the independent terms of both the numerator and the denominator to be 1. For this, in the numerator, we factor 20 and then we will have s over 20 plus 1. In the denominator, its factor is 50, giving us a result s squared over 50 plus 3s over 50 plus 1. The number obtained from the factorization is 20 over 50, and we multiply this by 40, being 16. To find the poles, we equalize the denominator to a general equation that is of the form s squared plus 2 zeta w 0s plus w sub 0 squared. W sub 0 squared will be equal to 3, making the clearance we obtain as a result 0.21, and these poles cause a peak from which we will obtain the value by means of the equation, and the result is 7.9 dBs. In the third step, we find the high or low frequency cutoff value that will be low frequency equal to W sub 0 over then at zeta is equal to 4.4 radians per second. High frequency equal is to W sub 0 over then zeta equal even 0.5 radians over second. Taking into account the calculations previously explained, we obtained this data. The orange line is a reference value for 0, while the blue line is the constant with a value of 24.08 dBs. We know that zeros in magnitude cause a slope of 20 decibels per decade. We can see in the pink line. As for the complex pole, it is denoted that it produced a fall in magnitude of 20 decibels per decade, and the peak located at 7.8 dBs is evident. Finally, the black line indicates the exact Bode diagram, linking the behavior of each value obtained in zeros, poles, and peaks from the indicate constant. On the phase diagram, the orange line also appears showing a zero reference value. In this case, the zero located at a minus 20 produces a slope on the straight line that rises up to 90 degrees, while the complex conjugate pole is shown falling to minus 180 degrees. It is important to note that direction at the poles and zeros in the diagram occurs from a decade before to a decade after the point at which each occurs. Finally, we obtain the black line that indicates the exact Bode diagram linking the behavior of each explained component.